All right, welcome back, everybody. We are doing this, we're continuing 1.5. We hadn't finished it yet. This is again Calc 2. So I'll call this 1.5B for the video and the upload of the notes. We are continuing. This was on continuity. And we had discussed what the three things were that made things continuous. And now we're just gonna do some more here with we're also gonna get 1.6 done today, and 1.6 is kind of long as well. Hey. Calc 1. Tricks ya. Thank you. So just a reminder real quick that for limits, for continuity, continuity at point C. A f of C has to be defined. B, the limit as x approaches C of f of x has to must exist. And C, that limit should be f of C. That implied continuity.
I say FCB has to be defined.
You get smart with me, Jacob.
I'm still dumb, so I'm not over it.
No, you're not.
Just a little bit.
You should never tell yourself that. Never talk down to yourself, folks. It's a reinforcing thing. Really is. Talk yourself up.
Yeah, Jim.
I do appreciate self-deprecating humor though, I do it all the time. Then we had, like, if it was continuous on a closed interval. This is all a quick recap. On closed interval AB, it had to be continuous. On the open interval. So everywhere between it said that every point in between, it's continuous at every point in between. And then the limit as x approaches A from the right of f of x has to equal f of A. And the limit as x approaches B from the left of f of x has to equal f of B. So the actual endpoints, really, this is like a special case scenario. Normally, we would require the limit to exist from both sides, or limit to be the same from both sides. But since these are the endpoints, we forego that and use one-sided limits. For those of you that are interested in the Mesa Center on Saturdays, it is now extended not from 9 to 12, it is from 8 to 2. I will be there for 6 hours. It's in room jam 124, but like that door's usually locked, it's in a hallway. Jam 108, if you've ever been to the Basic Center, it's like that side room that connects it. And that's directly open to the north parking lot. And you'll see the door is kept propped open. You'll see the door wide open in John Muir. 108. Yeah, it's 108. If you come in from the north parking lot, like if you park near the freeway. On that side, John Muir has like,
Northwest corner of the building.
yeah, it's the northwest corner of the building, there's a. Gate on the, like the middle of the building though, that's open, and you walk in the gate. If you look to the right, you'll see the door open. I'll draw a little picture afterwards. And the other fun fact that we mentioned, that people didn't like, and honestly, I don't like either. Continuous functions only need to be continuous on their domains. Like f of x equals 1/x is a continuous function. Despite. Having an asymptote at x equals 0. That's stuff we all said 2 days ago, maybe I like expanded on this with the green. Here, but like we said this all 2 days ago, but I want to refresh your memory because we're still looking at continuity and. If that shit's not in your head, what we're talking about, you're gonna be like, huh? This feels irrelevant. Anyone need this up longer? If you do, say something. Okay. I gotta read minds. Don't be like my wife, say something. Anybody else need it up longer? Alright. So stuff that's new. This is a theorem, they didn't give it a name, thank God. There are some dumb name theorems. I hate it when they give the name, the theorem, the name of the person that came up with it. Cause it never tells you what's in it, it's really hard to fucking remember. So if f and g are continuous. At x equals c. And k is a constant. Like a number. Then the following are true. The following combinations work. These are also continuous at c. This is a bunch of algebra stuff. Sum. F of x and g plus g of x. That's continuous at c. Difference. f of x minus g of x. Usually if something's true for addition, it's true for subtraction. Almost universally, because subtraction is just addition of the opposite. So it's still just adding. Constant multiple. K times f of x is continuous. You know, Kenyon, you stop bringing me donuts. This feels like a dirty trick. You remember how they're giving out donuts on the first day? She brought me a donut from outside. They said, I don't know how I guess someone knew. Maybe she said, I'm going to Professor Jones's class, and they're like, here, take him a donut, but she brought me a donut. I don't expect donuts, that was all just jokes. Products. Not your hair gel, f of x times g of x. And since products work, quotients work as well, because quotient is just multiplication by the reciprocal. Provided g of x does not equal 0. Of course, we don't want that. Well, let's say g of c. We're talking about continuity at the point. So we only need to worry about at that point. G of x can equal 0 elsewhere, but as long as we're talking about just c. Powers. Or exponents. F of x to the n is continuous.
Do we have to memorize?
Ideally. Some of it's just kind of like. If it's continuous, your algebra shit applies. And we're just listing the different algebra shit just to remind you what's out there. But it'll be. Hopefully intuitive at that point. And since powers work, roots work. Okay, roots are just an exponent. The nth root of f of x. This we do need to say, provided it is defined. On an interval containing c. And obviously, n needs to be a positive integer. We don't have negative roots, this seems silly. You guys ready for some more? Anybody need it up longer? All right, that page is going. All right, this example feels really fucking lame to me, but it's an example. Let's say if f of x and g of x are continuous. And f of 5 equals 7. Find g of 5 if we know that the limit as x approaches 5 of 2 f of x minus g of x equals 11. Feels like a made up problem just to make you think about what's going on. I can't ever see a situation where you have this kind of information. But it does kind of make you think about it. Well, remember how limits work? We can break this left side up into two limits. And I can actually factor the 2 outside. Bless you. And we know it's continuous function, so we can stick in 5. Continuous means that this is gonna actually equal. This will be 2 times f of 5 minus g of 5. Continuity says that those should be the same. That was our rule C. If it's continuous, the limit as x approaches c of f of x equals f of c. So we can plug it in. And we have f of 5, right? F of 5 was 7. So I'm going to, let's see, so I will add g of 5 to both sides just to get it by itself. And I'll subtract 11 from both sides. Right side is g of 5. The left side is 14 minus 11, which is 3. So g of 5 equals 3. Any questions? Not that exciting, was it? All right, let's do another limit or another theorem. If g is continuous at A. And f of x is continuous at g of A. Then the composite function f of g is continuous at A. And if it's been a while, remember log x means f of g of x. These are called composite functions, you stick one inside the other. Let's do an example. Find the limit as x approaches 16 of the natural log of the square root of x minus 2 over 6 minus the square root of x. Okay, so the idea here is we've got a lot of weird shit going on. We got a function, and then we got a bunch of shit going on inside the function. So maybe if we just define the outer function, let's say the outer function is the natural log of x. And then we say g of x is the inside. That's square root of x minus 2 over 6 minus the square root of x. Then what I have is f of g of x here. So we can break it up and look at it separately. Let's look at g of x. Let's see, at 16, let's just make sure they're defined there. At 16, we have a natural log of 16, it exists, I don't know what the value is, but it exists. G of 16, if we stick it in, it's not breaking any denominator, the bottom will be 2. So it looks like we can do it, let's do the limit of x approaching 16 of g of x first, because that's what we want to plug in. And there's no reason these are not continuous at 16. So we should be able to just plug it in. 16 minus square root of 16 minus 2 over 6 minus the square root of 16. Gives us 4 minus 2 on top. 6 minus 4 on bottom. I get 2 over 2, which equals 1. And now we take that and we stick that into f. So now we want the limit as x approaches 16 of f of 1. Which is the natural log of 1. And what's the natural log of 1? 0. Not that exciting. Not that intuitive either, you look at it, you're like, I don't know what the fuck to do there. So if you get to a problem where you're like, I don't know what to do, because like, maybe without the natural log, I would try to multiply by the reciprocal at the bottom or something like that. Well, now, just check first off, see if it plugs in and works, you never have to do any of the extra work, you plug it in, it works. But then like, well, what's the natural log doing? You could split it up, like break it up into parts. You guys ready for one of the more important theorems? It actually has a name that's applicable, it's called the intermediate value theorem. Someone wave in the middle of the room. Oh shit, there we go. This comes up often enough that you will see IVT. Stands for intermediate value theorem, obviously. So this is what the intermediate value theorem says. If f of x is continuous on a closed interval a to b. And if y naught or y sub 0 is any value between f of a and f of b. There exists a value c in AB such that y naught equals f of c. And that's a lot of words, but a picture is gonna make it go. When I show you pictorially what this is saying, you can be like, no shit. This seems fucking obvious. We got some graph. And I'll say A is right here. Which makes that f of A. And I'll say B is over here. Which makes that f of B. And then it says if y naught is any value between f of A and f of B. So we just pick somewhere between here, we'll call that y naught. It says if y naught is between f of A and f of B, there has to be some value x equals c. Maybe this is C1, C2, this is several spots here, C3. Where there's an x value that works. Now, even without seeing the graph. If I say f of A and f of B. A, B. And I have a point here and a point here, and a y naught here. F is continuous, right? That was the requirement, f of x is continuous, which means I can't lift my pin up if I connect the dots. Unless there's some weird domain thing. But even then, it wouldn't be defined at that, like if we did use 1/x, it wouldn't be defined at x equals 0. No matter which path I take to connect these dots, they gotta cross the line for y naught somewhere. That's all it says. If you're gonna connect the dots and it's continuous, it's gotta cross somewhere. Seems like a very intuitive thing when you like look at it that way. But it actually becomes really, really helpful and powerful, as you'll see in the next problem. You guys ready?
No, wait. Give me 1 minute to take a picture of it. There you go. I'm done. Thank you.
This becomes really helpful when we're trying to find roots. So what we're gonna do is prove that f of x equals x cubed minus 4x squared plus 5x minus 3 as a root. Now, there is no way for this one to not have one, because when you have an x cubed with a bunch of other shit, it's gonna look something like that. So it's infinite. The range is infinite. It's gotta cross somewhere. We know that. But we're gonna show it by using the intermediate value theorem. Roots, as a reminder, roots are where f of x equals 0. Let's call that our y naught. So if we can find two x values, a and b, we'll call, where f of a and f of b have opposite signs. By the intermediate value theorem. There is a C in AB where FC equals 0. And thus we have a root. Picture, it doesn't matter which way it is. If A is here and B is here, we could have one is f of A is positive, f of B is negative. It has to cross somewhere. Or it could be the other way around. F of A is negative, f of B is positive. It's gotta cross somewhere. It's gotta cross the y equals 0 line. Start with easy numbers. The easiest number to plug in and get a value for without a calculator is. That's an easy number, but not the easiest. 0. F of 0 is. All the x's go to 0, it's negative 3. But I like 1, 2. We're gonna check 1, 2. F of 1. We got 1 cubed, which is 1. minus 4 times 1 squared, which is minus 4, plus 5 times 1 is 5, minus 3. I think we still end up with a negative. So maybe we need to try something else. It looks like this is kind of like going up though. Maybe we try f of 2. See what we get. Maybe we'll get a positive there. 2 cubed minus 4 times 2 squared. Plus 5 times 2 minus 3. We have 8 minus 16. Plus 10. Minus 3. MF, this is still negative 1. Let's try another one, F3. Cubed. Minus 4 times 3 squared. Plus 5 times 3 minus 3. Let's see, 27. 4 times 9 is 36. Plus 15 minus 3. 27 plus 15 is 37, 42. 42 minus 36 is 6. 6 minus 3 is 3. So at 2, we were at negative 1. And at 3, we were at 3. So it's got to cross somewhere between there. There is a root. For f of x in the interval 2, 3.
Hey, where'd you get the 2?
I was just picking numbers. Picking numbers to plug in, that would make it like as simple as possible to calculate without a calculator. Right? The lowest, now I tried doing lower numbers, 0, 1 are the easiest. I wonder if negative 1 would work, it might have. It doesn't look like it, they all would have been negative, negative 1 definitely wouldn't work. And I avoided like fractions and stuff, so I was just picking whole numbers.
How does it work that 1 and 2 both come out to negative 1?
I'm guessing there's a root in there too. Maybe. But I don't wanna, like, we could look at it on Desmos. I get what you're saying, cause that's showing like we had f of 0 was down here. And f of 1 was here. So this is doing something like this, it could have crossed. But it might be doing something like that. I don't know, it could have gone up above and come down and done that. But like, I don't wanna check for like plugging in fractions is extra work, we just need to show one root existed. So I said, fuck it, let's just do another whole number, see if it crosses again. Or hell, it might have done something like this. There was a lot of paths it could have taken right there, we don't know where it was. But it did have to go up and down somewhere near there. Alright, there are problems like this. So this next one is tedious and you're gonna be like, eh. It's calculator work, that's why you're gonna hate it. Find the irrational root. Of f of x. Equals x cubed plus 3x minus 2. the 3 decimal places. Okay, so first off, we gotta find the region that it will have a root. Let's try 0 and 1 again. F of 0 equals -2. F of 1 is 1 plus 3 minus 2 is 2. So it's somewhere between 0 and 1. This is below and this is above. And they're both like equally apart, they're both 2 away from the 0. So maybe let's like try 1/2. F of 1/2 is 1/2 cubed plus 3 times 1/2 minus 2. So 0.5 cubed plus 1.5 minus 2. Negative 0.375. This one is also negative. So it's gotta be between 1/2 and 1. So maybe the next one we'll try is 3/4. 0.75. Six, 7, 1, that one looks like it's above. So we've already eliminated that region. And now we've eliminated that region. So we're between 0.5 and 0.75. I don't know, like 0.663 is in between them,
Are we looking like the zero for the 0?
we're looking for the 0. Or as close to 0, as long as we get within 3 decimal places.
Points, are we able to do something continuous, like 0.66, which would be 2/3?
Sure. You wanna try 2/3? Let's do 2/3. 2/3 is closer to 0.75, but that's fine. This is 8/27. Plus 2 minus 2 is just 8/27. That's handy. That's a simple division.
296.
So it's a positive number. So we're above it and we've eliminated that region. And what we're aiming for, our goal is to have, like our calculator shows 0.000 something. That's within 3 decimal places of a 0. So we're looking for the X there. So like this was 0.66, maybe let's try 0.58. negative 0.00, or not 00, but 0.6. So it's negative here. So we've eliminated that one, we're getting closer.
Six.
I like 0.6. Less decimals to plug into the calculator, let's try that. Get close. Point six is positive, we've eliminated that region. I'm gonna draw another number line here to blow up 0.58, 0.6. So I'll do like 0.59. And I'm gonna rewrite this, this was below, this was above. And I think you guys see what's going on, I don't need to write down what the formula is every time. Negative 0.02. We're still below. Questions? We've got two decimal places right now. We know it's gotta start with 0.59. We only need one more decimal place. I don't know, let's try 0.595. Told you weren't gonna like it. If I do f of 0.595. It's a negative number, -4 times 10 to the negative 3. So we're still below. So we eliminated that one. Two 0.597. Positive number. Nine seven is right there.
So my question is, the 10 you raise it to the power of 0.03.
That's
Negative
scientific notation. It means the -3 means move the decimal point left 3. And same thing on this one, 0.003. That shouldn't have an X in there.
So it's the same if I just put it -3, then
No, times 10 to the -3 is like doing negative, this is like -4 times 1/10 cubed.
yeah,
That's what
yeah,
that is.
yeah, I know, but I mean, it's the same if I, it is in -3, then use -0.03.
No. This negative, are you saying, does this negative make this negative?
Yeah, because you put a 0. That's the only thing I'm just.
The negative, it's because.
I'm just writing what the calculator shows. 0.3 is the same thing as 3.
Okay.
Sorry, now I understand the question. Yeah, the calculator, I get it. I didn't need the 0 there. I was writing what the calculator showed. Okay, so like, let's try 0.596. We're gonna see like which one it's between. We're almost done. This is negative 2.9 times 10 to the -4. That's a negative. So we're crossing off that one. It's between 0.596 and 0.597. We only need to do one more to see which way we round. It will try 0.5965. Cubed. And this is positive. So 0.5. 0.596. 0.597. 0.5965. 596 was negative. 597 was positive. 5965 is also positive, which means it's crossing in here. Which means this fourth digit is between 0 and 4. And it means we're rounding down. The root is approximately 0.596.
What is that? That's 0 to 4.
Yeah, I'm showing like what this fourth digit has to be. The fourth digit has to be something like that, and when we round down. Round down. We'll chop off that thing, so to 3 decimal places, we'll get that. But yes, if it wasn't clear, I wanted to be clear. And with that, let's take like a 10-minute break, and then I will torture the shit out of you with 1.6.